Shown below is a circuit containing a capacitor network. Let the values of the labeled components be as follows. C1 is 2 microfarads, C2 is 3, C4 is 4 microfarads, C4 is 6 microfarads, and the battery has a voltage of 10 volts. After that, we are asked to find the equivalent capacitance of the network, the charge on each capacitor, the voltage across each capacitor, and the energy stored in each capacitor. If you were an engineer and you were asked to design a circuit and somewhere within it was a network of capacitors such as this, likely you'd be fired. The reason is that these 4 capacitors act as a single capacitor. Why didn't you save the money and just buy one? Although there are rare exceptions to this argument, for the most part, capacitor networks are simply an exercise in understanding the difference between resistors or capacitors in series as opposed to resistors or capacitors in parallel. In our analysis of this problem, the key that we're going to use to make the problem as simple as possible is to be quite organized with regard to the solution. So, to do so, we will write a series of circuits, each of which is equivalent to the one in question, by replacing the numbered capacitors with a series of lettered capacitors. The first simplification that we come across is that capacitor 2 and 3 can be replaced by capacitor A. In this small sketch, I've left out the batteries for simplicity so that the sketches themselves can be more compact. The next simplification is to recognize that capacitor 1 and capacitor A are in series and can be replaced by a new capacitor that we'll call capacitor B. Finally, capacitors B and 4 are in parallel with one another, and we can replace those with a single capacitor known as capacitor C, and in this case we'll complete the diagram to show that the 10-volt battery is hooked directly across capacitor C. Because we recognize that for any given capacitor, the voltage across that capacitor is equal to the charge upon that capacitor divided by C, our organized analysis of the problem will be to make a table where the columns of the table are these 3 variables: capacitance of the capacitor, voltage across it, and charge upon it. Finally, in this problem, as opposed to the ones that I showed in lecture, we've been asked to find the potential energy stored on the capacitor, and so I'm going to add a 4th column to this table, and the last column I'm only going to calculate in the case where we're analyzing a real capacitor. And the real capacitors are, of course, capacitor 1, capacitor 2, capacitor 3, and capacitor 4. The organization follows by putting the equivalent capacitors, A, B, and C, into the same table and recognizing that we can calculate every quantity of every capacitor. We'll label our columns in accordance with their units. We'll use microfarads for the capacitance, volts for the voltage, and therefore the calculations will be simplest since V equals Q over C, so Q is equal to C times V if we list our charges in microcoulombs. We've been given 2 microfarads, 3 microfarads, 4 microfarads, and 6 microfarads as our starting value, and it's time to calculate the equivalent ones. Capacitor A is made out of capacitor 2 and 3 in parallel, and in parallel the capacitance that you get as the total is the sum of the 2 values, so adding capacitor 2 and 3 we get a total of 7 microfarads. Capacitor B is formulated by the series combination of capacitor 1 and capacitor A, and here's where we put in a little bit of thought while we calculate. Capacitor 1 is 2 microfarads. Capacitor A is 7. If you were to place 2 equal capacitors in series, the result would be half the value. So, 2 copies of capacitor 1 in series would give us 1 microfarad as the total capacitance. 2 copies of capacitor A in series would give us half of 7, which is 3.5 microfarads of total capacitance. Since we have used one 2 microfarad capacitor and one 7 microfarad capacitor, we expect our answer for this capacitance to be between 1 and 3.5. And if we perform the calculation, we find the answer of 1.55, where the 5 5s continue to repeat. Finally, for capacitor C, we recognize that this is formed by a parallel combination of capacitors B and 4, and in parallel you sum the capacitances, so this gives us 7.55 microfarads as the total capacitance. Finally, we have a capacitor where we know what the voltage is. That capacitor is hooked directly to the 10-volt battery, so its voltage is 10 volts. If we ever get 2 out of 3 of V, Q, and C, since V equals Q over C, we can calculate the third. So therefore, equivalent capacitor C has a charge equal to C times V, and we're going to get 75.55 microcoulombs. Now we begin the task of dismantling our previous calculations. Capacitor C was formulated out of a parallel combination of B and 4, and the thing that is the same for any two items in parallel as well as their equivalent capacitor is the voltage. Therefore, we will copy the 10 volts of capacitor C into the row for capacitor B and capacitor 4. And now each one of these two rows has two values, so we can calculate the third. Multiplying by 10 is easy. So we see that capacitor B is going to have 15.55 microcoulombs, and capacitor C is going to have 60 microcoulombs. At this point, we perform a check. Since the voltages were the same from this parallel combination, the charges must sum. And indeed, the 60 microcoulombs on capacitor 4 added to the 15.55 on capacitor B is equal to the 75.55 on capacitor C. This gives us reassurance that we haven't made a mistake in our calculations, and we can move on to disassemble capacitor B. Capacitor B is formulated by a series combinations of capacitor 1 and capacitor A. All elements in series will have the same charge. Therefore, the charge on capacitor A will also be 15.55 microcoulombs, and so will the charge on capacitor 1. Each time we fill 2 out of 3, we can calculate the third, and so the voltage in each case is going to be Q over C, yielding the following results: 2.22 bar volts on capacitor A and 7.77 bar volts on capacitor 1. Again, we perform the checksum. 2.2222 added to 7.777 gives us the 10 volts of capacitor B that was broken apart in this step, so we again gain confidence that we have done this calculation correctly. Finally, we recognize the capacitor A itself was formed of a parallel combination of capacitors 2 and 3, and therefore, since we know that voltages are the same for all items in parallel, we can copy the voltage from capacitor A of 2.22 volts into capacitor 2 and capacitor 3's column. Q is equal to C times V, giving us 6.66 microcoulombs on capacitor 2 and 8.88 microcoulombs on capacitor 3. Once again, we do not fail to double check our checksum. Since the voltage was the same on 2 and 3, the charges must add up. If we add the 6.66666 to 8.88888, we do get 15.55 microcoulombs, and this gives us tremendous assurance that every calculation we have done up to this point is correct. On an exam like this, you don't get partial credit because there's no work shown on the page. Therefore, please, please, please reference the checksums to see that your totals work. Finally, now that we have the voltage and charge on every capacitor, we can calculate the potential energy. There are 3 possible ways to calculate the potential energy. We could calculate the potential energy as 1/2 QV, or we could calculate the potential energy as 1/2 CV squared, or we could calculate the potential energy as 1/2 Q squared over V. I don't care which one you do, you're going to get the same answer either way. That answer, we will note, it will be in microjoules to make things simpler, and the numbers we get are 60.49, 7.41, 9.88, and 300 microjoules on all these capacitors. Just for fun, we can perform one final calculation. We can calculate exactly the same thing for the single equivalent capacitor and come up with 377.77 microjoules. And if you check, adding together the stored energy of capacitors 1, 2, 3, and 4 adds up to the stored energy of the equivalent capacitor, again demonstrating that we did these calculations correctly.